Okay, so this is also from a past exam. I believe this came from fall of 2019, but I am not, yeah, fall of 2019. For my current statics class, we have not done uniform loading yet. Okay, we haven't done that. We're going to be heading to that after this exam. So please don't freak out about this. I'm going to simplify it and make it a point load so that we can do this problem. So I want to calculate the support reactions at A and C due to the loading shown, and I can see I have an applied moment and I have this uniform load, which we're not going to worry about. I'm going to make it a point load for you, okay? And I want to find the reaction at A and C, which are pin. So if it's pin, I know that I'm looking at at a X and Y. And when I look at this, I can see 1, 2, 3, 4. I have 4 unknowns, okay? I have 3 equations of equilibrium. How am I going to do this? Well, I do have an internal pin at B, okay? So that's an internal pin, so I know I can take it apart. It even tells me. Does it tell me that I have a pin at B? It's pinned at point B, so I know that. But I also can recognize that this is a 2-force member. And as a 2-force member, if this is pushing, we can see that this is going to be pushing down. This has to be pushing back up all the way through because it's a 2-force member. So that already tells me before I get started that my X and Y components are going to be pushing in that same direction, okay? And this is going to be 3/5 force in BC, 4/5 force in BC. So even without looking at a pin here, I've now simplified this to AX, AY, and BC. 1, okay, because they're just relationship 2, 3. So I can do this problem without taking it apart, or I can take it apart at B and do it that way. So the first thing I have to do is I'm going to draw an overall free body diagram. And I would just get used to, as a student, like going through here and it's telling you we're support reactions at A and C. I have to find my reactions there, okay? Member BC is pinned to ABD. It tells me it's a member BC and ABD. I shouldn't be cutting it in weird things or making weird little tiny beams. It's telling me it's member ABD. It's this whole thing, okay? So overall, I have an unknown AX. I have an unknown AY, okay? I have this applied moment here at the end, 1200 Newton meters. And I have, here's my strut coming down at like this, and I know this is going to be 4/5 BC, and this should be 3/5 BC because the magic of that 2-force member. Okay, this is 2 meters, this is 1 meter, and again, it doesn't really matter how far down this comes. It could come down 4 feet, 3 feet, 40 feet, 30 feet. It's all relational. Okay, it's all relational. This, we're going to find out next week. The area under that curve, remember we're moving in integration. Well, if it's a rectangle, I know that the area is base times height. So I have 3 meters times 600 newtons per meter, and I get 1800 newtons. Okay, so now we're a point load unit. And I know for a rectangle that the centroid is right in the middle. So 1800 newtons right through the center. If this is 3 meters long, this is 3, my base is 3 meters, then I know that point load is 1200 newtons. And we're at 1.5 meters, 1.5 meters, which means that we are then 0.5 meters over to B. Okay? So this direct is right here that would be 0.5. Okay? So now that's, too many unknowns. I can't do this, except you could, because these are relational to each other. So I know if I have an internal pin at B, I can draw a free body diagram of ABD. And when I do that, I'm going to have 1200. I'm going to have unknown AX, unknown AY, moment of 1200 Newton meters. Okay, and this, if we are pushing up on a 2-force member, we are pushing back down. Okay, pushing back down. Doesn't matter how we want to do this. So I'm going to have my 2/4 member. I have 3/5 BC. I have 4/5 BC. So equal and opposite, pushing down and to the right, which means when I'm looking here at this pinned connection, I'm pushing up and to the left. Down, down, up, left, right, equal and opposite. When I put it back together and look overall, I don't see what's going on at B. Okay, so I know this is 1.5 meters over 0.5 and 1 meter. I also know that this is going to be 4/5 BC and this is going to be 3/5 BC. So now, and this would be my free body diagram, BC. So I'm going to use free body diagram, ABD. And when I look at this, if I sum moments about B, straight through these right at that point, I can solve for AY. So let's sum the moments about B equals 0. So if I have a clock handle and I'm looking at AY, so I've got my clock handle, I'm pushing up, okay, negative rotation, so I have negative AY times 2 meters, okay, clock handle, 1200 going down, okay, positive rotation plus 1200 newtons times 0.5 meters, okay, these go away, and then I have minus 1200 Newton meters, and all of that equals 0. So I'm going to pull this over to get rid of that negative, so I have 2AY equals 1200 times 0.5 is 600 newtons, okay, minus 1200 Newton meters. That would actually be meters when I use my units. So I get 2AY equals negative 600 Newton meters, which means AY equals negative 300 newtons. And the negative tells me, my numbers don't seem right here. So I have 1200 times 0.5. I have 1200 times 0.5. 0.5 times, that's 600. I have this 1200 Newton meter, so 1200 minus is 600. And then this is 2 over 2 divided by, and I get 300. That is not what I'm seeing over here. Hold on. Oh, I'll tell you why. Because I cannot copy to save my life. 1800, I don't know where that came from. I don't know where that came from. This is just like the story of me doing math. I drop things all the time. Okay, I just constantly dropping. So that means this is actually 900, which means this is actually 300, which means this is actually 150. And this is kind of an important thing when it comes to grading. 500 newtons. So I have AY equals 150 newtons, and it's going down because it's negative. The important thing about grading is one of the reasons we ask you all to draw free body diagrams to be consistent in writing your equations is because if you make a mistake of, okay, I found the correct point load, but then somehow, because I was sloppy and didn't read that that was an 800 and I thought it was a 200, I brought this 1200 over instead of the 1800, then we know that's where that mistake came from. If you did this in your head and you said 6 times 3 is 1800 and then you wrote 1200 and we didn't have that work, we would be like, we don't know where that came from, you're going to lose more points. And this is why it's just super important to identify what you're doing and learn to be neat with it, so we can follow from simplifying a load to drawing a free body diagram to what's going on in your sentence. It's not really your sentence, but it's your equation, but it's like your math sentence, okay? And so I got AY down 150 newtons. If you had done that on a test, we could have said, they just miscarried over. We would have said, that's called a carryover. That's a carryover. They carried over a mistake. Everything else is right. 24 out of 25. We're not going to ding you for the rest of it as long as it's correct, because we can follow where it came from, okay? So I have AY is 150 newtons down. So now I can either come back over here, and I like to just go ahead and call that 150 newtons down. And here I could sum forces Y. I could sum moments about this point and get AX. I can use this member right here. I can sum forces Y. I can sum forces, once I get Y, I can get X because of that relationship, and then I can move down here. So again, this problem can be worked 4 or 5 different ways. If you're struggling with this, just redo, work it every which way you want to. So I'm going to continue with my free body ABD, and see, I've got it labeled. This is coming from this free body diagram. It's very clear where it's coming from. And now I'm going to sum forces in the Y direction, and I get a negative 150 newtons. That's from my AY, okay, minus 1800 newtons. That's coming from that applied load, okay, plus 4/5 BC. That's coming from the Y component of this strut. That's a moment, it doesn't matter, equals 0. So I'm going to get that 4/5 BC equals 1950 newtons. So BC equals 5 times 4 divided by 2,437.5 newtons. And it's positive, so when I said it was up here and down here, then I made a correct assumption, okay? If BC is 2437 positive, I can now find, I can still use this, and I can say, well, at BC, okay, if BC is 2437.5, then I can find that the X component is 3/5 of 2437.5 newtons. 3 times 5 divided by, and I get 1462.5 newtons. Okay, so now I've looked at this little nugget right here, recognizing that it's a 2-force vector. And once I have the force in this vector, I can calculate X and Y. So it's X. And now I can still go back up here, and I can sum forces in the X direction equals 0. And I get AX minus 1462.5 newtons equals 0. So AX equals 1462.5 newtons in the direction that I assumed. Okay, so we can go back up to our overall picture, 1462. Well, when I look in the X, I can see that 3/5 BC ought to equal that, which that's what I got. But more importantly, as I'm pushing down on this, this strut is having to push up to keep it in place. And if it's pushing up, the X and Y components are pushing, how do I do that? Are pushing this way. And if they're pushing this way, I've got to have this X component pushing back equal and opposite. Okay? So it's making sense behaviorally. If I know AX is 1462.5, I can go to my overall free body diagram. Okay? I also know I've already calculated right here, I already calculated the X component. So that is my X component, 1462. I also know what the Y component is. I can look at the overall. I can sum forces in the Y direction. I can take the Y component is 4/5 of BC. I could look at my 2-force member. Okay, there's multiple ways that I can actually look at this problem and see, am I getting the right answers? Am I not getting the right answers? What is going on? So I will tell you that CY equals 1,950 newtons. It was positive, so it is going up. And I should be able to take AY and CY, not AY and CY, CY and CX. Okay, so I know that this was 1462. I know that this one was 1950. And it's a 2-force member, so I should be able to take 1462, square it, 1950, square it, add them, square root it, 2437. That's the magnitude in that vector. And that's why we spend so much time at the beginning of the semester breaking vectors into X and Y and trying to understand the X and Y components, because really this is just, it's a vector. Okay, it's a vector that is a strut in this figure holding everything up. Okay, so I hope I didn't confuse you too much with going from 1800 to 1200, but I knew something was wrong. And I would have found out at the end when I went back and made sure my work made sense.